Welcome to the Explainer. Today, we're going to demystify the foundational process of estimating electrical load for offshore platforms. I'm going to show you exactly how this is a rigorous, highly structured mathematical journey and absolutely not just guesswork. We are literally laying the bedrock for every other electrical decision made on a project, so let's jump right in.
Imagine you're handed a blank sheet of paper and told to design an entire plant's power system. Where do you even begin? Well, the stakes are incredibly high here. Getting it wrong leaves you with two terrible options. You either face catastrophic power failures because your system is undersized, or you're looking at massive financial waste from buying unnecessarily oversized gear.
Okay, let's take a quick look at the agenda. We'll cover why load estimation matters, classifying plant electrical loads, the motor margin rule, calculating total running load, the N-1 sizing philosophy, and finally, a complete worked example and summary.
Starting right off with Section 1, why load estimation matters. We really have to start with the foundational logic behind aggregating power needs before we do anything else. You literally cannot select a single cable, transformer, or generator until you have this baseline established.
And there's a great analogy that brilliantly illustrates this concept. Think about building a house. You wouldn't size your water main without knowing exactly how many taps and showers might be running at once, right? Well, we have to scale up that exact same logic of concurrent usage to an entire offshore electrical grid.
Moving to Section 2, classifying plant electrical loads. Let's see how this builds our baseline by putting every piece of equipment into specific operational buckets. You can't just throw everything into a single spreadsheet column and sum it up.
First up, we look at the load's urgency in two dimensions. We start with safety and production priority. We categorize loads as vital. Think life safety, UPS, and emergency lighting. Then we have essential loads, which keep the core process running, like your main compressors. And finally, non-essential loads, which honestly won't impact safety or immediate production if you happen to lose them.
Next, we cross-reference those priorities with their physical duty cycles. Basically, how often do they actually run? We classify them as continuous, meaning they are always on, intermittent, meaning they cycle on and off, or standby, which means they only run when a primary unit fails.
That brings us to Section 3, the motor margin rule. The absolutely crucial point here is that you never, ever take a machine's required power at face value. This is a classic trap that a lot of novice engineers fall into. We have to build in a safety buffer. Your selected motor rating must always be physically larger than the driven machine's bare requirement. Why? Because the motor needs extra torque to overcome static friction during startup and to accelerate the load without totally overheating. Now, veteran engineers actually use a kind of insider cheat code for this. Depending on the physical size of the motor, you add a standard margin. It's usually 125% for small motors up to 15 kilowatts, 115% for mid-range, and 110% for large machines above 55 kilowatts. So if a pump needs 90 kilowatts, you multiply by 1.10 and size the motor at 99 kilowatts. That naturally pushes you to select the next standard size up, which would be 110 kilowatts.
Section 4, calculating total running load. Once all our individual loads are classified and correctly sized with those margins we just talked about, we are finally ready to aggregate them into our total electrical footprint.
Now, don't let the math intimidate you. It's actually quite elegant. This equation simply applies a diversity factor to account for a really basic reality. Not every single motor, light, and heater runs at 100% capacity at the exact same time. If we sized our system for absolute maximum concurrent draw, it would be massively overbuilt.
To get a realistic total plant running load, we estimate the true draw by taking 100% of our continuous loads, so a factor of 1.0. We then take only half, or a 0.5 factor, of our intermittent loads, and we completely zero out the standby equipment since it isn't running during normal operations anyway.
Moving to Section 5, the N-1 sizing philosophy. With our total kilowatt number safely in hand, we now reach the absolute cornerstone of all oil and gas power system design. This is exactly how we guarantee resilience.
We absolutely have to design for the worst-case scenario. Out at sea, you can't just call up the local utility company for backup power. This introduces the N-1 philosophy. If N is your total number of generators, the remaining N-1 generators must seamlessly take on the entire plant's load if one of them suddenly trips.
To survive that sudden failure and the immediate spike in power demand on the remaining units, industry standards dictate your generators should normally cruise at a comfortable 70 to 85% load factor. This leaves them just enough headroom to absorb the shock of a failed pier without tripping the whole system offline.
But remember, our load schedule gave us a number in kilowatts, which is real power. Generators, however, are rated in kilovolt amperes, or apparent power. This requires us to divide our total kilowatts by an assumed power factor. Typically, that's 0.87 for low-voltage systems or 0.89 for high-voltage systems.
And finally, Section 6, Worked Example and Summary. Let's bring this all together and prove out the math on our blank sheet of paper, step by step, so you can see exactly how this works in actual practice.
Okay, let's apply our diversity factors to a hypothetical plant. First, we take our 3,200 kilowatts of continuous load and multiply it by 1.0. Next, we take our 800 kilowatts of intermittent load and multiply it by 0.5, giving us 400. And our 1,500 kilowatts of standby load gets multiplied by 0. Add those all up, and we easily arrive at a total plant running load of 3,600 kilowatts.
Next up, we take that 3,600 kilowatts and divide it by our assumed low-voltage power factor of 0.87. We punch that in, and that yields exactly 4,138 kVA of required generation. That right there is the absolute minimum size of our power plant just to run the daily operations.
Now, let's test our N-1 philosophy. Say we install 3 2,500 kilowatt generators, and one of them suddenly fails. The remaining 2 must carry that full 3,600 kilowatt load. The math shows our load factor spikes to 72%. That lands perfectly safely in our target zone of 70 to 85%. Disaster averted, and the lights stay on.
To lock this masterclass in, here is your 6-point survival checklist for load estimation. Remember to classify in 2 dimensions, use your 1.0, 0.5, and 0 diversity factors, always add your motor margins, convert with the correct power factor, and rigorously test against that N-1 philosophy. Definitely keep this checklist handy.
So, we've now perfectly sized the required power for our plant, but that leaves a massive, provocative question for our next explainer. How do you actually generate thousands of kilowatts of electricity in the middle of a hostile ocean? We'll dive into the massive machinery that makes it happen next time. Thanks for learning with me today.